Hi everyone, I'm Daniela Weir and I'm going to be teaching your lecture on data analysis and reporting for pharmacoepi studies. I'm sorry I'm not able to meet you all and join you in class in person, but online I suppose is what we all have to do right now. So, just wanted to give a little bit of background about me before we get started with the lecture. So, I'm an assistant professor in the Division of Pharmacoepidemiology and Clinical Pharmacology. I'm an epidemiologist by training. I just started with the division in July of 2021, and I moved here from to the Netherlands from Canada. So I'm really enjoying spending time living in a new country. I have a bachelor's of science in biological sciences from the University of Alberta, as well as a master's of science in epidemiology from the same university, which is in the province of Alberta in the western part of Canada. I have a PhD in epidemiology from McGill University in Montreal, and I also completed my postdoctoral fellowship at the University of Toronto. So, just a little bit about my research interests. My position is 70% research and 30% teaching. So, my past research to date has mainly focused on the safety of medications among older adults with multiple chronic conditions. I've done a little bit of work in diabetes medication safety and did a few drug utilization studies. And I've also looked at ways to improve the safety of medication use for patients in the transitions between hospital and home. And I've helped develop a patient-centered application for that. So yeah, my research is obviously mainly drug related, and have a diverse experience in this area that I've acquired over the past 10 or so years. So I'm going to actually take my video off now that I've gotten to say hello to you guys, because it actually gets in the way of the slides, and I don't want to keep moving it around for the rest of the lecture. So today, what we're going to focus on covering are descriptive statistics. What are they? How to do them? We're going to look at power calculations, missing data. What is it? How to deal with it? We're going to look at inferential statistics, statistics that we can actually make conclusions off of. We're going to quickly touch on subgroup analyses as well as sensitivity analyses. We're going to look at some different options for statistical software. And then we're going to quickly discuss presenting results kind of throughout all these different topics, and quality of reporting for observational drug studies. And I'm also going to end with a demo in SPSS. And I'm not an SPSS user. I haven't used SPSS in probably about 10 years. So I'm going to say that the demo, I bet you there's a lot better SPSS demos you can find on YouTube online. I kind of point and clicked around and did my best. And I think I demonstrated what you guys are going to be doing during your analysis. But I think you'll notice how easy it is for you to figure out the software and look things up when you don't quite seem to be able to know which options to use. So yeah, so I think that's it. I just want to mention that if you have questions about this lecture, any part of the materials, any additional questions on data analysis or anything about the SPSS demo, you can post it in a comment underneath where I'll be posting this in on the Teams page in Microsoft Teams. You can post the question there and I'll be happy to answer it there. Or you can email it to me and you can either look me up or I'll include I think I have a slide with my email on it at the end of the lecture. And feel free to email me if you'd rather ask your question anonymously, and then I can just post the question and answer on the within the comment section on Microsoft Teams anonymously as well. So whatever you feel most comfortable doing. Okay, so what I'm going to try and do for this lecture is I'm going to try and use this published study on diabetes medications and the risk of liver disease in order to kind of demonstrate all of the principles I'm going to be teaching. Because I know when I was learning statistics and data analysis, I always found it hard to just learn the theory and not relate it back to a concrete example. So I'm going to try and do that the best I can. I do want to say that this is not a statistics lecture, a formal statistics lecture. I'm kind of teaching you the bare bones or the basics of data analysis with a little bit of statistics in there, but it's important for me to point out that if you are doing a complicated statistical analysis or you want to learn more about statistics, you should take a statistics course or consult with a biostatistician. Like, this is not enough for you to go off and do a complicated pharmacoepi analysis for publication. Let's say this is enough, just a primer to get you started and help you figure out what's important for your for the analysis for your report. But if you're really interested in this, you should really take a biostatistics course or an advanced methods course, or consult with a biostatistician, because, as I said, I'm not going into the nitty-gritty details of the theory, and I've simplified a lot of this just so it's a little bit more digestible. So okay, so moving along to the example paper. So I'm going to be switching between the example paper and the PowerPoint presentation for the rest of the remainder of the lecture here. So the example paper is called thiazolidinediones, which I'm going to refer to as TZDs because that's quite a mouthful, and glucagon-like peptide 1 receptor agonists and the risk of non-alcoholic fatty liver disease, a cohort study. So the background and aims of the study, so the quick background was that TZDs and GLP-1s are potential pharmacological treatments for diabetes for patients at risk of non-alcoholic fatty liver disease. I'm just going to refer to this as liver disease for the remainder of the lecture. Therefore, the authors examine the association between the risk of liver disease and the use of TZDs and GLP-1 receptor agonists compared with the use of sulfonylureas and insulin. So for all of my my examples, I'm just going to focus on the TZD SU comparison and the risk of liver disease, just to simplify things a bit. So quickly, this is all just part of the abstract of the paper, and again, I'm going to post the paper in the section that I post the lecture video in and the recording. So for this study, the authors conducted a population-based cohort study, and everyone should know what that is from Olaf's previous lecture, using primary care data from the Clinical Practice Research Data Link database, which is from the United Kingdom, between 2007 and 2018. They selected or studied all patients aged 18 years and older with a prescription of a oral glucose lowering agent or GLP-1 receptor agonist in their study cohort. And they started follow-up at the first prescription for those medications. And the primary outcome was a new diagnosis of liver disease. So these were incident cases of liver disease. They used a Cox proportional hazards regression model to estimate the hazard ratios and 95% confidence intervals for the primary outcome. And I'm going to get into what a Cox model is later. They calculated the incidence rates per 1,000 person years for all exposures, and I'll get into how you calculate rates later. The study identified 207,367 adults with a prescription for a glucose lowering agent. The risk of liver disease they found was lower in patients prescribed a TZD than those prescribed an SU, and they drew this conclusion based on calculating an adjusted hazard ratio of 0.32 with a confidence interval of 0.2 to 0.51, and I'll talk about adjusted hazard ratios later on. So those are the main results of the study. So I'm just going to give a quick summary of the study for the purposes of using this as an example moving forward. So patients again. This is the study, how we create the study question using our PICO. So the population was those that were 18 and older with a prescription for a diabetes medication. The exposure or the study medication of interest was TZDs. The comparator was sulfonylureas. The outcome was liver disease, and the mean follow-up time was about 5.1 years. I've included some examples of confounders that were included in the study here. So alcohol use, BMI, and categorize BMI, and I'll get into the differences between these different variables later. There were also a lot of other confounders that were considered in the study, but just to simplify things, I'm just going to look at alcohol use and BMI to teach a few different statistical concepts here. Okay, so the first thing that usually you need to conduct when you're doing a statistical analysis or data analysis is you need to look at which descriptive statistics you want to conduct. So a lot of people like to rush into kind of the complex statistical modeling, adjusted results, but really the descriptive statistics are the most, one of the most, if not the most important step of a statistical analysis, because it really lays the foundation for a quality analysis, which is really quite important, very important when you're conducting data analysis. So what's the first thing you want to think about when you're approaching an analysis? So what's the first thing you want to do? Well, the first thing you really want to do is get to know your data. So you really want to understand what variables you have in your data set, whether the values make sense. Can you actually ask or answer the scientific question of interest with the data that you have access to? How you're going to handle missing data, and how you can best summarize the study sample. So the purpose, just to elaborate on this a bit further, of descriptive statistics is to look at, for simple summary statistics, to help understand distributions of your variables and look for problems. So first you want to look for missing values in any of your data. So you want to look to see how are they coded. Sometimes when you get a data set, the missing values will be coded as a period, but sometimes they'll be coded as like a 99 or a 999. And you really want to make sure that any missing variables are not actually coded as a valid response in your data. So that's important. You want to look at data quality. So you want to look at whether variables have predictable distributions. So for example, if you want to look at something like gender, if you want to look at something like age, let's say, and you have a maximum value of, let's say, 500, you might start to think there might be an issue with that particular variable, because there's no way you're going to have an age distribution that goes up to 500. That indicates there might be an issue in your data. So these initial descriptive steps help you understand issues like that. You want to check the units, so you can determine whether weight is in kilograms or pounds, or whether it's a mix of both. You look at the distribution of those variables to figure that out. You can also look at univariate statistics, so you can describe particular variables one variable at a time, and I'm going to describe how we do this in the next slides. And you can also look at things like bivariate statistics. So these include things like cross tabulations or scatter plots to look at associations between two different variables. Oops. So first, I'm going to start off with the different types of data or variables that you might come across in your data sets, or data that you want to use to answer a particular study question. So the first are numerical variables. So this type of data can be discrete numerical. So this includes things like the number of pregnancies or a number of infections, or it can be continuous. So this would be a continuous numerical variable would be something like weight. And typically you calculate means for these variables. So from our example study that I outlined in the first part of the lecture, BMI is a continuous numerical variable. So the second type of data that we're having access to is a binary. Sorry, I just had to pause there for a moment. So another type of data that you might come across, or a variable, is binary, a binary variable. So this type of data only has two possible values. So this includes things like a yes, no response, gender or sex, so whether you're male or female. It's usually easier to assign numbers to these particular to this type of data. So it can be a 0 or a 1. That's why it's called a binary variable. So if 1 is equal to, or yes is equal to 1 and no is equal to 0, yeah, and you can do the same for gender. You can calculate, typically you calculate proportions for these variables. Some people say you can calculate means for them as well, but that's really dependent on the type of binary variable you have. Typically, you calculate counts, n is equal to the number of subjects in your study with that particular characteristics, and the percent is of the total study population. So in our example study, alcohol use is a binary variable. So you're either an alcohol user, yes or no. Another type of data that you might come across are categorical data or categorical variable. So categorical data typically has a finite number of possible values, which indicate different categories. So this can be something like, for example, marital status, where you could be single, married, cohabitating, common law, separated, widow, all these different options, but there's not an infinite number of options for your marital status. It's only a finite number. So that's a categorical variable. Categorical data can also be subdivided into ordered and unordered data. So ordered data tends to be something that has it's kind of ascending or descending. So something like marital status, you can't really order being single, married, cohabitating in any sort of sensible way. But if you're looking at something like a categorical variable for the, if you've categorized the number of pap smears someone might have, and it's 6 ordered categories, then you can say, someone's had 0, 1, 2, 3, 4, 5, 6. Each of those is a separate category, and you can order those by ascending or descending order. So that's important to understand. You don't typically calculate means or differences for categorical variables, but you can calculate, again, the n percent of subjects with that given characteristic within your overall study population. So from our example study, BMI was categorized into 5 categories based on a continuous measurement. So I'm actually going to go to the study and show you that right now. This is going to be part of the table 1, which I'll describe more in detail. So we can see here, a bunch of patient characteristics are listed in this table. If you go to BMI, we can see that it's actually listed as a continuous numeric variable, because they report the median in the overall study population, which is here, but they also categorized it here. So you can see they've categorized it into less than 20, 20 to, here I'm going to make this a little bit bigger, 20 to 24.9, 25 to 29.9, 30 to 34.9, and greater than 35. Is how they categorized our the continuous BMI variable. So now that we've talked about the different types of data and variables that you might come across in a data set to answer a question related to drug safety or effectiveness, we're going to talk about how we actually display this information, both in table format and graphical format. So to start off with, we're going to look at how we can display a single categorical variable. So going back to our BMI example, we can do a cross tabulation of BMI, which is where we show the N% for each BMI category for the entire study population. So the total number of people in the study population, as I mentioned for our example study, is about 207,000 people. And here in this cross tabulation, we can see that 1.3% falls into this BMI category, 11% falls into the 20 to 24.9 category, and so on. You don't always have to report the N, because you can obviously calculate the N based on the percent if you have the overall study cohort. So that's a cross tabulation. What you can also do is convert the information from this cross tabulation into a bar graph. So this is just really simply a graph with the frequency on the y-axis and the BMI category on the x-axis. So all the categories we saw in the previous table are listed here, and then just the frequency is listed in the bar chart. So as I mentioned, about 1.3% of the study population had a BMI which was less than 20. So this is just a graphical way to display the cross tabulation for a particular categorical variable in your data. You can also display a single numerical continuous variable using a histogram. So this looks very similar to the previous bar graph, but instead of having the BMI categories on the x-axis, you have all the possible BMI values in your data set. So all of the continuous values in your data set. So for the histogram, all you have is the frequency or the count of each unique BMI value in your study sample. So this just is going to show, for example, if this is the 20 category, how many people in your study sample had a BMI of 20. So that's a histogram. So a box plot is another way to display a single numerical variable as well. So we're going back to our continuous, our BMI is a continuous variable example. So what we see here on the y-axis is the total range of the BMI values. And in this box here, we represent the median, which is this line here, the 25th percentile, which is this line here, and then the 75th percentile, which is this line here. This is typically the range, so the maximum and the median, or the maximum and the minimum are located here, and sometimes, depending on the software you're using, you'll see outliers, which is just denoted by that little star there. So that's a box plot. Another way to, and this is very similar to a histogram, I probably should have put these slides side by side, but another way to display a numerical variable is using a probability density curve. So again, we're using BMI as a continuous variable as our example. And a probability density curve just essentially draws a smooth line over the histogram. So just shows the relationship a little bit more easily than a histogram might. So another way to display a numerical variable. So typically, when we're actually conducting our statistical analysis, we're usually only going to use a crosstab in the actual paper. These sorts of graphs, sometimes you'll include them, sometimes you won't. It really depends on the study, but these are typically done for you just to understand your data a bit better. So just because you run one of these graphs to understand the distribution of a particular variable doesn't mean you're going to include it in the results section of your report or your scientific paper. You have to pick and choose which graphs you're going to include to kind of tell your story and support the answer to your research question. You're not always going to display all these graphs, so just keep that in mind. And you'll get a better sense of that when you look through some other example papers. However, how you summarize a numerical variable, that is always reported in a scientific paper. So the way you can, there's two ways you can summarize numeric variables or numerical variables. This includes the mean and the median. So the mean is just the average. So it's the sum of all the values of a particular, for all the patients in your sample, divided by the total number of subjects. And the standard deviation is a measure of the spread or variance around the mean. And you can calculate these measures using whatever statistical software you decide to use. I'm not going to give you all of the formulas for the standard deviation or anything like that in this lecture. You don't need to know again the theory behind it. Just know that standard deviation is a measure of variance around the mean. You can also calculate the median and just really simply put the, did I forget a scatter plot? Oh no, that's later on. The median is really simply put the middle number in an assorted ascending or descending list of numbers. And you typically want to calculate the median when you have a lot of outliers in your study, because the mean is very sensitive to outliers. So with the median, usually you also calculate the interquartile range, which is the measure of dispersion around the median. And you're going to typically report the 25th percentile and the 75th percentile. And as I said, it's not really sensitive to outliers. So it's best to use this if you do have a lot of outliers in your study, which you typically determine by looking at the graphs here. So you'd know if you have outlier values for a particular variable based on something like that. So that's another reason you want to do these descriptive statistics. In our example study, median BMI for the overall study cohort was 31, and the IQR was 27 to 36. So I'll just show you how that was actually reported in the study here. So as I mentioned, we have the BMI, and this is the column here. I'll just go like that for the overall study cohort here. And the report, the BMI is 31, and the interquartile range here is from 27 to 36. So that's how a median would actually be included in a table of baseline characteristic results. Okay. So now we're going to go on to how we actually would display and understand two different variables at a time. So previously we're just looking at single variables at a time. Now, and those were univariate statistics. Now we want to look at that bivariate statistics, where we actually explain the relationship between two different types of variables at the same time. So if we want to display two categorical variables at the same time, we can again do a crosstab. So if we go back to our example study and look at categorized BMI, we see it's presented overall, but it's also presented according to the type of diabetes medication. So TZD users and SU users. So you present the N% for each category of BMI according to the type of diabetes medication. So for this column here, you would calculate, this would be the number of people, or this percent is 0.8. And how that was calculated would be the total number of people in the TZD group that also fell into this BMI category divided by 2,104. So it's the proportion of people in the TZD group that fall into that BMI category among all those in the TZD group. So these cross tabulations again can be done in whatever statistical software program you're going to use. So this is very similar to what we described previously. You can also display two categorical variables using a side-by-side bar chart. So from our example study, as I mentioned, we can display categorical BMI according to the type of diabetes medication they're taking. So could see here that in the TZD group, let's look at the heaviest BMI category here, the 35 and over. So about 30.5% of TZD users fell into this category, whereas about 15.5% of SU users fell into this BMI category. And you can see that here in the side-by-side bar chart where we have the percent on the y-axis, the frequency on the y-axis, or it's just the percent rather, on the y-axis and the BMI category on the x-axis. And here we can see we have TZD users in blue and SU users in yellow. And as we can see here, the 30% is here and the 15% is here. So we can see that there's a greater proportion of within the TZD group that are in a higher BMI category compared to the SU group. You can also use something called a scatter plot in order to display two continuous variables. So a scatter plot is really simply just a diagram that displays values for two variables for a set of data. So each dot in this scatter plot represents a single patient. So you have continuous variables on both the y-axis and the x-axis. So this is just an example, not from our study, our example study, but related. We have systolic blood pressure on the y-axis and we have weight on the x-axis. So each dot represents a single patient and their weight and their systolic blood pressure values, and you just plot them. So usually, and statistical software can do this for you too, but if you're doing a scatter plot, you can actually plot a line of best fit through that data to understand the relationship between these two variables. So you could determine, for example, if people with increasing weight also had an increase in their systolic blood pressure. You can also display a continuous and categorical variables together using side-by-side box plots. So I explained what box plots were in a previous slide, but essentially what you do is instead of plotting the box plot for a single variable, you plot it for each category of your categorical variable. So this again is just an example, but you're going to have your continuous variable on the y-axis, and then you're going to have your categorical variable on the x-axis. So here I just have the number of metabolic syndrome features and the body mass index on the y-axis. So for each category of the number of metabolic syndrome features, I can describe what the median, or visualize rather, what the median and the interquartile range, min and max values are, and any outliers for each of the categories for BMI. So for example, we can really easily see here visually that those with three or four metabolic syndrome features tend to have a higher median body mass index compared to those in the 0 to 2 category. And this is just a straight line here because I don't think there's very many people in this category here. So that's a side-by-side box plot. Okay, so now we've gone over how to describe single variables for continuous binary and categorical outcomes, how to combine these different types of variables into bivariate statistics. Now I'm going to talk about how we actually take those results and use them to describe our study population in a scientific report or a scientific article. These are typically called baseline descriptives, where we're describing our study population. So I'm actually first, let me see here. I think first I'm going to explain this and then we're going to go back to the paper. So in the results section of a scientific article or report, typically you have results in tables and figures, and then you have it in the body of the results section of the text. So typically when you're presenting the results of descriptive statistics for your baseline characteristics, in the body of the text, you're going to include information on the overall study population size, the mean or the median follow-up time if it's a cohort study with the standard deviation or interquartile range. You're going to describe the number of people and the percent of people who are exposed, the number and percent of people who are in the comparator group, general baseline characteristics, which I'll show. So things like median and mean age, the proportion of males and females, etc. And then you're going to comment on the differences in characteristics between your exposed and your comparator groups. So you also include this information in a baseline characteristics table. So first you would probably make this table and then you would describe it in words in the body of the text. So what I'm going to do is I'm actually going to switch over to the paper here, and we can we can look at the results. So I'm just going to go back. So we already talked about the abstract and we looked at the main results. This is just the background of the paper, materials and methods, study, all of that would be part of the lecture that Olaf taught you, as well as like how to prepare a protocol. That should all be part of Olaf's lecture. So we're more going to focus on the data analysis section and the sensitivity analysis and the results section, as well as the tables and the, there's just 2 tables for this, and we're going to skip over the, yeah, there's 3 tables for this, and then skip over the discussion section. So first, I'm going to show you how they describe the analyses that they're going to, I think that actually should be part of Olaf's lecture on the data analysis. He should have talked to you guys about all of that, I believe, but maybe I'll quickly go over it. So, no, you know what? I'm just going to go straight to the results and we can talk about that other stuff later. Okay. So we can see here in this sentence, they say a total of 207,367 patients met our study inclusion criteria. So that's describing the overall study size, mean follow-up of 5.1 years. So that's the duration of follow-up. Now they're talking about the characteristics of the study. So they say the median age of all users was 61 years and 45% were female. So that's really important for describing your overall study population. Now they are going to talk about, and I think, did I include this in the, yeah, so maybe I didn't make this super clear initially, but these baseline characteristics are also really important to discuss differences in characteristics between your exposed and comparator groups. So in this study, we're looking at differences between TZD users and sulfonylurea users for the main study population. So here in the body of the text, they start going into whether there's differences in baseline characteristics or descriptive characteristics between TZD users and sulfonylurea users. So they say here at baseline, users of TZDs were younger, and they have the age in brackets there. Median age had a higher BMI, a lower hemoglobin A1C, and whatever that was, and fewer diabetes related complications when compared. Okay, they just talk about insulin users there, but we can also look at this in terms of differences between TZD users and sulfonylurea users from your table 1. So here we can see we have all of our baseline characteristics listed here. So we have continuous, categorical, and binary variables in there. We have the overall study population, as well as this is the study drug here, TZDs, compared to SU users, which is the comparator. So we have proportion of females in the study cohort overall, and then stratified according to TZD users and SU users. So for example, if I wanted to look at something like age, we can see here that median age in TZD users was 61 and the median age in sulfonylurea users was 66. So I could say that sulfonylurea users tended to be slightly older compared to those using TZDs. So that's just an example of how we would display the descriptive statistics for the baseline characteristics in the body of the text in the results section, as well as in the table 1. Hi, everyone. Okay, now we're going to move on to the next section on outcome descriptives. So for the first part of this lecture, we described patient characteristics, mainly how to present different types of patient characteristics, baseline characteristics for a study, how to describe our study population, and all of the summary statistics, graphs, and such in order to do that. Now we're going to move on to how we actually describe our study outcomes when we're conducting an analysis for a drug safety study or a similar related study. So what we're going to look at are a few different measures of interest. And then again, I'm going to be going between the lecture slides and our example paper related to the association between TZDs and liver disease in order to solidify some of these, a few of these concepts and make them a little bit more applied. So some of the measures of interest we might be interested in for our study population that we're following forward in time. We're going to be, how many people were followed, how long were people followed for, and how many people had the outcome. So I'm going to go to the results section of our study paper. So we followed 207,367 patients for a mean duration of follow-up of 5.1 years. What was the other one? How many people had the outcome? So I think that's a little further down here. Overall, 2,526 patients were diagnosed with liver disease during the follow-up. So that just links it back to our example paper here. So a measure of occurrence that we can calculate in order to start describing our outcome of interest is the risk. And the risk is calculated as the number of cases of a disease divided by the total number of people at risk. So it's a probability. So this is typically how, just a little example of how the data would be set up in order to calculate something like this. But I'm actually going to go back to the study paper to show you how I would calculate risk. So for TZD users and for sulfonylurea users and overall. So if I wanted to calculate the overall risk of liver disease, it would be, so there were 2,526 liver disease events divided by the total number of people in the study cohort, which I'll just use this number here. It's just 207,367. So that's how I would calculate risk overall. If I wanted to, so that's just an example of how risk is calculated. So then we're going to move on to another measure of occurrence, which is common in cohort studies when we have person time of follow-up for each subject, which is the incidence rate. And this is calculated as the number of new cases of a disease divided by the total person time of follow-up. So person time is defined as the time each person spends in the follow-up until they experience the outcome within your cohort of interest. So this is really important because it accounts for different periods of time under observation, because it's very rare, unless the follow-up time is very short, that we follow all subjects for the entire follow-up time. And it's also important to account for the fact that people are no longer at risk once they experience the outcome, and they have to stop contributing to the total person time of follow-up. So this is just an example graph with people that we're following. So this is just the start of the follow-up. We follow people forward in time. This person had an event at year 3. This person we're following forward. They were only followed until year 3, but they didn't have an event. So what we can do is we can, in order to calculate the incidence rate, we can add up all the person years of follow-up for each person. So it's 3 years, 3. I have the calculation here. total time at risk is 31 years. There's 2 cases we can see here. So the incidence rate is calculated as the number of cases divided by the person time of follow-up, which is equal to 0.06 events per person year follow-up. So I'm going to go back to our, our research study to show how I would calculate this using the numbers here. So we're going to go to table 2 here. So in table 2, what we have is for each diabetes medication, again, we're just going to focus on the top 2 medications here. They have listed for sulfonylurea users and TZD users the total number of events and the total person years of follow-up here. So in order to calculate this, so this is the incidence rate per 1,000 person years of follow-up. This is called the incidence rate. You can just call it the rate as well. It's called the incidence rate because these are new or incident cases of liver disease. So in order to calculate the incidence rate of liver disease among sulfonylurea users, we would divide 616 divided by 172,309 person years of follow-up and multiply that by 1,000, which would equal 3.6 events per 1,000 person years of follow-up. So that's how I would calculate the rate or incidence rate for the outcome among sulfonylurea users. Okay. So we also want to understand other measures of interest we want to look at are how many people were exposed to the study drug, which we can call drug A, how many people were exposed to drug B, which we can call a comparator. And in our example, drug A would be the TZD, drug B would be the comparator, which is sulfonylurea. How many people exposed to the drug had the outcome, and how many people exposed to the drug B had the outcome. So we want to be able to arrange this information in a 2x2 table. So we would look to see, you have the exposure on the left-hand side here for the rows, and then you have outcome up top for the columns. And usually it's arranged as drug A versus whatever the comparator is, and then the outcome, yes or no. So you just call these cells with the numbers for each A, B, C, and D. A plus B is going to equal the total number of people treated with drug A, and C plus D is going to be equal to the total number of people that are using drug B. And obviously A plus B plus C plus D is going to be the total study population. The number of people, the outcome is going to be A plus C, and the total number of people without the outcome is B plus D. So just shows how we can arrange all this information and put it into a 2x2 table. So what we really want to know, so actually I'm going to go back and show you how I would do this with our example. So I already talked about the overall event rate, but here to calculate the risk of the outcome in SU users, it would be there's 616 liver disease events in the SU group. So to calculate the risk of liver disease among SU users, it would be 616 divided by the total number of people in the SU group, which is 21,732. And then if I wanted to calculate the risk of liver disease among TZD users, it would be the 18 events in the TZD group divided by 2,104, which would give you the risk in the risk of the event in the TZD group. Okay, so the other measures of interest we're interested in looking at is to determine what the occurrence of you want to determine whether the occurrence of the outcome was more likely among those taking drug A compared to those taking drug B. So in other words, we would want to know whether the risk of liver disease was higher among those who were treated with TZDs compared to those who were treated with sulfonylureas. So in order to achieve this or answer this question, we want to measure something like a disease rate or risk or odds in exposed people compared to unexposed people or the comparator group to determine if the exposure is associated with that particular outcome. So in order to do that, we can calculate things called measures of association. So these include things like risk ratios, incident rate ratios, odds ratios, risk differences, and rate differences. So a risk ratio and a risk difference, how we would go about calculating that. So first of all, we would calculate the risk of the outcome among those taking drug A. So that would be calculated according to our 2x2 table as A over A plus B, which is the total number of people with the event treated with drug A divided by the total number of people treated with drug A. Then you would calculate the risk of the outcome among those taking drug B. So that would be the number of events. It would be C over C plus D. So this is the total number of people with the outcome who are taking drug B divided by the total number of people taking drug B. And that would be the risk in the drug B group. So in order to calculate the risk difference, it's the risk of the outcome in the drug A group minus the risk of the outcome in the drug B group. And then the risk ratio is going to be the risk of the outcome in the drug A divided by the risk of the outcome in the drug B group. So back to our example study, we would calculate the risk of the outcome in those taking TZDs, and then the risk of the outcome, liver disease, in those taking sulfonylurea. And we'd either take the difference between the two risks or we take the ratio of the two risks. Excuse me. So the other measure of association we can look at is rate ratios and rate differences. So typically these are what you want to calculate when you have a person time of follow-up, and this is what you would include in your study. When we go back to our example study, you see that there's no risk ratios or rate ratio, or there's no risk ratios or risk differences or risks really reported. They just have incidence rate ratios and then associated adjusted hazard ratios, which I will describe later on. So the rate, so in order to calculate the rate ratio and the rate difference, first you're going to calculate the rate of the outcome among those taking drug A, which is A over the total person time of follow-up among those taking drug A. And then you would calculate the rate of the outcome among those taking drug B as the total number of events in those taking drug B divided by the total person time of follow-up among those taking drug B. So you can either take the ratio of those two rates and the difference, or the difference of those two rates. So what I'm going to do is show you an example of this in the our example study paper. So this is our table 2. Recall we were able to calculate the incidence rate of liver disease among SU users and the incidence rate of TZDs among, the incidence rate of liver disease among TZD users. This is incidence rate per 1,000 person years of follow-up. So we're comparing TZD users to SU users. So what we do is to calculate the crude or unadjusted incidence rate difference. We subtract we go 1.2 minus 3.6 to get the incidence rate difference. And to calculate the incidence rate ratio, we would calculate, we would go 1.2 divided by 3.6 to get the incidence rate ratio. So this is the crude or unadjusted rate ratio, and the difference is the crude or the unadjusted rate difference, and these are the crude rates essentially, is what these are, because these are typically like interchangeable. These terms are used interchangeably: unadjusted, crude, and then the rate ratio and rate difference, or and I just explained that here. So crude or unadjusted results. So when we actually want to talk about, actually present this information in in our paper, in our report or our scientific manuscript, we usually include it in the body of the text. So we describe the risk ratios or the crude or unadjusted rate ratios overall. And then according to each medication that we're comparing, the study drug and the comparator. And then we also typically include it in the table 2. So I have table 2 here. So this is what we would include in the table. And then we typically would include this information in the body of the text as well. Okay. Okay, so our next section is related to power calculations. So in the first part, we talked about descriptive statistics and describing our study population. We also talked about how to describe our outcome of interest within our study population. So after we do those just initial descriptive steps where we know like the number of, we look at the patient characteristics, we might look at, what might be important to adjust for in our analysis. I'll get to that a little bit later on. We look at the number of events that we have. What we actually want to know is whether we have adequate statistical power in order to answer our research question of interest. So there's different ways we can go about doing this. So power and sample size. So this is an important part of any research study because if our precision is too low, we don't know whether or not our results are due to chance or whether there's a true relationship between our study drug and our outcome of interest. So power is defined as the chance of finding an effect when there is a true effect. And typically, the larger the sample size that we have that we're working with, the greater the power to detect whether to detect the difference, um, if there's a true difference between, or if there's a true effect between the study medication and the outcome. And this means that we have better precision. So examples of small versus large sample sizes. So for example, let's say we have a Cox model where we're estimating the strength of the association between age and survival among cancer patients. So in the full data set, we might have 213 patients where 151 died. We have a hazard ratio which includes 1.022. Confidence interval is 1.003 to 1.042, and the p-value is 0.023. So we would be adequately powered to detect this difference in this study because because we do detect a difference. And the p-value is greater than 0.05 for this particular study. However, if we had half as many patients in this study, where we only had 100 and 74 died, the hazard ratios are quite similar through 1.22 versus 1.024. However, the confidence interval does cross the null, and our p-value is greater than 0.08, which would suggest that there may not be an association between age and survival time. Just not because a true association didn't exist, which we can see from the first part of these results here, but only because we had a smaller sample size and we had less statistical power. So overall, the more data you have, the more power you have to detect a real difference. So sample size calculations are typically essential for prospective studies. So this includes randomized controlled trials and prospective observational studies, because you actually have to determine how many patients you need to enroll in the study and how long the study has to go on for. But sample size calculations for cohort and case control studies are a little bit more complex and a little less useful for retrospective cohort studies. For retrospective cohort studies, we tend to do power calculations because we tend to use all of the data that's available in a given data set. And usually what we do is we take the data and we can actually calculate the power we have to detect a particular effect of a medication on a particular outcome, or whether a medication is associated with a particular outcome after doing our analysis. So just to give an example of what you guys would do for your own studies in order to calculate statistical power, I took examples of a few numbers from our study example study. So here, the number of subjects in the study was 207,367. We had 2,526 events. The overall probability of an event was 1.2, which I calculated again from the study. 1.2%. The subjects in the TZD group, there were about 2,000, meaning the proportion of study population in the TZD group is 1%. And the hazard ratio we were looking at was 0.32. So typically the hazard ratio we'd include in a power calculation we don't typically have we wouldn't have conducted the study already to know this. Typically we'd look at previously published studies in order to get like an estimate of what a reasonable hazard ratio is. So I'm going to actually go in and show you how I would have gone about doing this. So this is a website. I've included a link for it in the slide. So what I do is I'm going to go to a power calculator and I'm going to find the appropriate one. So we're using a time to event analysis in the example study. So we're going to look at a Cox proportional hazards, two-sided equality power calculation. So then it shows, so we're not going to calculate the sample size, we're actually going to calculate the power, because as I mentioned, usually we start off with a pre-specified sample size, and we want to calculate the power we'd have to detect an association between the study drug and the outcome, if a true association does exist. So we select the power, we'd add in the sample size that we have. Power, we'd leave it. So typically this is like always 80%. So we'd leave it as is, and the error rate is always 80%, we'd leave it at 5%. So these are fixed variables. So I would have put in the hazard ratio. So this would have been 0.32 from our study example. Overall probability of an event, this was 0.012, I believe. Portion of the sample in group A. So that was, I called that the TZD group. So what was the proportion I had in there? I have it in the slide, but I just want to show you guys. It's 1%. So it's 0.01, 0.01. So I can go in and calculate that. And where's our power? Calculate. Did it not work? Oh, I forgot to put in my sample size. Include that. There we go. Calculate. So we have 0.999 power. That's what we're calculating here. The error rate is going to be fixed at 5%. And our power. So I would have said that for that particular study, we are adequately, like 80% power is a good, is typically what's deemed adequate. So we had 99% power to detect a hazard ratio of 0.32 if it actually exists. So I just mentioned again down here that using administrative data for a retrospective cohort study, you usually have a set sample size. So what you're going to do is you're going to fill in your set sample size. This is based on pre-existing studies usually. Pre-existing studies, those are going to be your best guesses for what you think you're going to get in your study. Leave the error rate at 5% in order to calculate the power. Okay. So to kind of further elaborate on this, when we actually want to include other variables in our statistical models, what we want to know is how much data is enough data in a retrospective cohort study. So sample size, even though we already start off with a pre-specified group of patients, sample size is still an issue in retrospective cohort studies. So if we're using a multivariable regression model, like a Cox model or a logistic model, which I'll explain more in detail later on, these models tend to become unstable if there's too many covariates that we're including in the models and not enough outcomes. So this can often result in really large confidence intervals and actually result in biased results. So this is kind of a rule of thumb, is typically what you want to do is you want to have 10 outcome events for every covariate in a model. So like going back to our example study, we want to have at least 10 liver failure events or liver disease events for every covariate we included in our statistical model. So if we don't have enough events,
So as I was saying, what do you do if you don't have enough? You have too many confounders and few outcomes. So there's a few, and you might be underpowered for your statistical model. So how to select confounders and all of that will be more clear in the next part of the lecture. But what you want to do is you want to check to see how many outcome events there are and determine whether there are at least 10 events per covariate. And if there are, and you calculated your power previously and you have adequate power, you can proceed with your analysis with all the identified confounders. If not, what you can do is you can exclude confounders from the model, weak confounders based on statistical analyses. You can exclude less important confounders using backward selection, or you consider the use of a propensity score. And these are all going to make a lot more sense when I talk about variable selection for multivariable models later on. But just know that if you don't have, excuse me, if you don't have enough events for the number of confounders, you don't have enough statistical power to conduct your analysis, there are things you can do to deal with this. Okay, so just a quick word on missing data. You guys don't need to worry about missing data in your analyses. You should probably just very briefly describe it, but with respect to conducting any analyses to deal with missing data, don't worry about that, but you should just know what it is and why it's important. So what we want to do in the descriptive part of your analysis is to determine what proportion of data is missing. And typically what happens when you have missing data is you use something called multiple imputation by chained equations. That's the best method to use. But data has to be missing completely at random. In other words, it can't be linked to missingness of another variable. Just note the complete case analysis is not typically appropriate, where you only analyze subjects with full data because it can lead to biased results. So it's best just to describe it for your reports. Don't worry about dealing with it in the analysis, but just know it's important and you should describe it in your own reports. Okay, we're going to move on to our next section on inferential statistics. So what is the purpose of inferential statistics? So overall, formal inferential statistics allows us to make probability statements about the conclusions made, therefore giving some measure of the strength of the evidence in favor of a particular hypothesis. So this is just a bit of a fancy way of saying you're going to associate statistics with the probability that a medication causes a particular outcome compared to another comparator medication. So typically what we do to use that is we calculate adjusted measures of effect. So I'm going to describe those in a bit. But more simply, what we're going to start off with are a few statistical tests. So these are just for unadjusted analyses when we just want to look at straight differences between two different variables without accounting for confounders or other important variables in the analysis. So if we want to compare a continuous variable between two different groups, we might want to use something called a t-test. So a t-test assesses the statistical significance of the difference between the average of a continuous variable for one group compared to another group. It's essentially what it is. And you're trying to reject the null hypothesis, is that there's no difference between the means of the two different groups. You want to compare a continuous variable between more than two groups, what you can use something called an ANOVA. So that's used to assess the statistical significance of the difference between the average values of a continuous outcome across more than one sample. And again, the null hypothesis for this specific statistical test is that there's no difference in the means of the two groups. So typically what you end up with for a t-test as well as an ANOVA is a p-value indicating whether there's a statistically significant evidence or whether there's a statistically significant difference in the average of a continuous variable between the two groups. If you want to compare two proportions, typically what you could use is something called a chi-squared test. You just want to know if there's a difference in proportions between two groups. There's other tests as well, and you can look those up, but the chi-squared is more different. So again, this is going to give you a p-value for whether there's a statistically significant difference in the proportions between different groups. And you can run all three of these tests in the statistical software that you're going to use. So you can run a t-test, an ANOVA, and a chi-squared test within SPSS or something like that. So now we're going to move on to regression models, which are a little bit more complicated ways of, which is a more complicated way of conducting inferential statistics. So why do we want to use multivariable models in the first place? So in the previous slides, we kind of outlined how we can compare the crude risk or rate of an outcome between drug A and drug B. So why don't we just stop there in order to answer a research question of interest? What we could do is we could calculate the crude risk ratio or the crude risk difference, crude incidence rate difference, and then conclude, why don't we just conclude based on that information whether there's an association between drug A and our outcome of interest compared to our comparator. Well, we know based on lectures from Olaf that confounding is an issue and we need ways to deal with it. So in drug safety studies, this is more specifically called confounding by indication. So we know that prescribing isn't a random process, and those who were prescribed a particular medication or drug B might have actually already failed an earlier treatment, like drug A, for example. And these two groups of patients likely have different characteristics compared to one another. So a lot of the time, when there's different levels of treatment for a given condition, people who are on more progressive forms of treatment tend to be sicker, older, whatever, compared to people who are on first line treatments. But then when you're comparing a first line treatment to a third line treatment, this comparison is going to be confounded by indication. So from our example study, we wanted to determine whether there was a difference in the risk of liver disease among those using TZDs compared to those who are using sulfonylureas. So those taking different diabetes medications tend to be different than each other with respect to things like age, BMI, and other existing chronic conditions, which are all characteristics which are also related to the risk of liver disease. So in order to deal with this confounding, we tend to use a statistical adjustment within a model, or analysis of variance, it's called, to deal with confounding. We typically use this over stratification because statistical models are easier to deal with multiple confounders at the same time, as well as continuous variables. So examples of models or statistical models include multiple linear regression, which you tend to use when you have a continuous outcome variable, logistic regression when you have a binary outcome variable, Cox proportional hazards models when you have a time to event outcome, and Poisson models when you have count outcomes. So logistic regression, really Cox proportional hazards models are the most common in medication safety studies, because if you have a binary outcome, you can use logistic regression only, but you tend to only use it if you don't have time to event data or follow-up data for each patient. In this type of analysis, you're assuming patients are all followed for the same amount of time, which tends to be a bit difficult and lead to biased results in drug safety studies. Typically, we use Cox proportional hazards models. So how does multivariable regression work? So typically, regression allows us to estimate the association between exposure and outcome while holding other variables constant or adjusting for other variables. So when we talk about exposure and outcome, we're talking about something like our medication of interest and our outcome of interest. So going back to our example study, this would be TZD use and liver disease. So this is just a statistical model which outlines what regression is. So this is the outcome, this is the intercept, and then these are all of the covariates which are in the model, the x variables, and these are the coefficients, the beta coefficients, which which are attached to each of the variables, and it indicates the association between a given variable and the outcome of interest. So this could be the exposure variable, and then these could all be the confounders that you're including in the model. So how do we actually select confounders? Actually, I really should know. I'm going to mention this later on. So how do we select confounders to include in our multivariable models? So we have to include confounders, first of all. So these are variables that are associated with both the exposure and the outcome. And I think Olaf mentioned this in his lecture. So how do you actually determine which variables are confounders for your research question? So it really does depend on whatever problem you're looking at, but you really need to understand the subject matter. Using purely statistical tools in order to select confounders typically leads to biased results. So you really do need to look up the subject matter, and there's different ways you can do this in order to determine what confounders are for different health-related questions. Intermediates should not be included in the model. So intermediates are variables that are on the intermediary path between the exposure and the outcome. So for example, let me think about this for a minute. So sun exposure can cause cancer, and mutations in, let's say, the DNA in the skin or something is an intermediate between sun exposure and cancer. So level of, let's say, DNA mutation would not be a variable that you'd want to adjust for in a statistical model if you're looking at the association between sun exposure and skin cancer. Additionally, covariates that are associated with just the treatment but not the outcome should not be included in the model because these are not confounders. Confounders are variables that have to be associated with the exposure and the outcome. So other ways to select confounders to include in our multivariable models includes things like exploratory graphs and summaries might help you understand, how to include a variable in a model. So this would include, should I include a variable as a continuous model, or should I include a variable as a continuously in the model? So age, should we categorize this, or should we leave it in as a continuous variable? These are things that you need to look at descriptive statistics first in order to make this decision. You can also, for continuous variables, don't worry about this for your analysis. This is a bit complicated, but for continuous variables, sometimes like a linear relationship is inappropriate to assume between that particular variable and your outcome. Sometimes you want to use more flexible ways to model continuous variables, but don't worry about that for your particular analysis. Just focus on whether you want to use measure particular variables, a binary, categorical, or continuous outcome. But overall, it's best if you're trying to adjust for a confounder, it's best not to categorize continuous variables because you tend to lose information. Okay, so I'm going to focus in on two different types of models that are typically used for pharmacoepi studies. So this includes logistic regression. So recall, we use logistic regression, and this is something you can run in whatever statistical software that you're going to be using. So when you use logistic regression, when you have a dichotomous outcome, yes or no, it doesn't incorporate information on time to event, as I mentioned. And as I'm here, if x1 is the treatment variable, then the beta coefficient associated with this variable will indicate what the association is between the exposure and the outcome variables. So if the odds ratio is greater than 1, exposure increases the odds of the outcome compared to the comparator. The odds ratio is negative than or less than 1, the exposure decreases the odds, and if the odds ratio is equal to 1, there's no association between the two. So the beta coefficient in a logistic regression model, if this is your exposure variable, this is going to be the odds ratio for the association between your exposure and your outcome. Another important variable, and this is the most commonly used model in most pharmacoepi studies, is a Cox proportional hazards model, and it's used when you have time to event data. So you have whether you've experienced an event, yes or no, as well as the follow-up time for each individual. Typically used in cohort studies. Again, we tend to use these models because it accounts for loss to follow-up and people leaving the risk set, and accounts for the fact that not everybody is followed for the same length of time. So this is a Cox proportional hazards model. This is the outcome here. This is the baseline hazard function. You don't need to worry about what that means. So what you need to know, again, is similar to the logistic regression. The beta 1 coefficient here, if this is the exposure variable, beta 1 is going to be the hazard ratio, which indicates whether there's an association between the exposure and the outcome. The hazard ratio can be interpreted like a risk ratio, but it's a little bit different. But don't worry about that for now. A hazard ratio, if it's greater than 1, similar to an odds ratio, there's going to be an increased risk of whatever outcome you're looking at compared to your comparator. If your hazard ratio is less than 1, there's a decreased risk of the outcome associated with your exposure compared to your comparator medication. And if the hazard ratio is equal to 1, there's no association between the two. So just keep in mind that for both the logistic regression model and the Cox proportional hazards model, you can run both of these in your statistical analysis software. And don't forget, what you want to also calculate is the confidence interval around your hazard ratio and your odds ratio for each of these models. You pick one or the other. You either do a logistic regression model or a Cox proportional hazards model, depending on the data you have access to. But if you're going to calculate the hazard ratio from the model, make sure you get the confidence intervals around each of these hazard ratios. So I'm going to go over how you present the results from your multivariable models within our example study, and I'm going to do that right now. So in the results section, let me find it here. Patient characteristics. Okay, so here it is here in the body of the text. So typically what you want to show is, okay, here it says current use of TZDs was associated with a decreased risk of liver disease when compared with SUs. Okay, so they report the, look at that out of the way, the adjusted hazard ratio, which is the AHR, which is 0.32, because it's less than 1. We know that there's a decreased risk of liver disease compared to the comparator medication, which is sulfonylureas. And here we report the hazard ratio, 0.2 to 0.51. It doesn't include the null, or it doesn't cover the null, which is 1. So we know that there is a decreased risk of this outcome associated with TZD. So that's the way you would present it in the results section of the text, and then you also present it in your paper, or in the table. So remember, we were talking about all of the unadjusted rate estimates in the incidence rate estimates in the table. Well, now we can look at the adjusted hazard ratio here with the 95% confidence interval. So this is TZDs, which is here, versus sulfonylureas, which is the reference, and this matches what we saw in the body of the text. So that just demonstrates how you interpret the hazard ratio, how you present the hazard ratio and the 95% confidence interval as part of the results section of your study. So I just went over that here quickly, that in the body of the text, you want to present the adjusted odds ratio or hazard ratio with 95% confidence intervals based on the output you get from running your either logistic regression model or Cox proportional hazards model. You also want to provide interpretations of these estimates with respect to the comparator. So I was talking about the fact that TZDs are associated with a decreased risk of liver disease compared to those using sulfonylureas. And this is because the hazard ratio is less than 1, and the confidence interval doesn't cover the null or include the null, which is 1. And you also want to include these in a table of results, which I already showed you. Okay, I copied it there and there. Very good. Okay, so I'm just going over this very, very quickly because we mentioned it a little bit in the power calculations, and you'll see this in a lot of pharmacoepi studies. I don't expect you guys to, and you're not expected to do a propensity score analysis in your statistical methods, but you just should know about it. So as we mentioned in the power calculation section, sometimes you have too many confounders to adjust for and not enough events to have adequate statistical power in order to detect a difference between whether there's an association between your study medication and your outcome, if a true association exists. So in order to deal with that, we talked about potentially using a propensity score in order to account for this issue. So essentially, all you do in a propensity score is that you include all your confounders of interest in a model where the treatment is the outcome, and then you adjust for this score in your model alone in order to account for confounding. You can also stratify by the score or match on it. And if you're really interested in learning more about this, you can look at this paper here. But just know a propensity score is something to an overall score that you adjust, stratify, or match on in order to adjust for a large number of confounders. Also, one other kind of complicated statistical or analysis issue for pharmacoepi studies, which don't expect you to actually implement in your own studies, but it's really important to just know about if you come across it in any other scientific papers, is that most of the time when we're looking at medications, medication exposure, as you know, changes over time. It's not a time fixed variable. So a lot of the time, what you do in statistical analyses is that you actually model medications as a time varying variable, where you look at, changes in medication use or non-use over time. And that's typically implemented in your statistical analysis. So just know that that's a thing. Just if you come across it in a paper, you'll have heard about it before. There's lots of background information on this, but just a note on time varying exposures. I think this is actually part of, I believe this is part of the, it might have been described in the methods section of our example paper here. Let's look here. This would have been in the exposure to glucose lowering agent section. So here, follow-up time is divided into fixed intervals of 90 days. This how time varying drug exposure was defined is explained in this entire section here. So when I mean time varying drug exposure, this was all outlined in this section here. And this also would have been evident in the type of statistical analysis that was outlined. So we talked about time-dependent Cox proportional hazards models. That means you have a time-varying drug exposure. So that's why they talked about that in the data analysis section. Okay, so now that we've described all of these different methods, it's really important that you actually are able to outline these in the method section or the data analysis section of your protocols. So essentially, what you're going to do is you're going to talk about the statistical analyses that you undertook to get all of the results that you just described. So typically what you want to do is you want to talk about how you calculated your unadjusted incidence rates, the type of statistical model you use. So they talk about a time-dependent Cox proportional hazards model, the variables that were adjusted for in your analysis, that you calculated adjusted hazard ratios, what all of your comparisons were should be included in the data analysis section. And how you selected your confounders should be included, which confounders you included in your final model. Those are the sorts of things that you should include in your data analysis section. Essentially, it's just an overview of the statistical analyses you conducted that would provide enough information that anybody else trying to replicate this analysis would be able to do that as well. So just a quick last few slides here on subgroup and sensitivity analyses. So sometimes when we're looking at the effect of a medication in a particular population, it could be that the effect of this particular medication might differ between different subgroups. And this is called effect measure modification or heterogeneous treatment effects. So, for example, maybe it could be the case that a diabetes medication might be more effective in people with high blood pressure compared to people with lower blood pressure, stuff like that. So, if you have a biological reason or background or a hypothesis that there might be differential treatment effects between two different subgroups, there's two different things you can do um, to include this in your analysis. You can do a subgroup analysis where you present the main results of the analysis separately for example, people with high or low blood pressure or younger or older individuals. So you would just reconduct your analysis in like younger people alone or and in older people alone or in males alone and in females alone. And then you would report the odds ratios or hazard ratios for each of these groups. You can also include an interaction term in the model, which is actually the best way to go about doing that. That's just what the statistical model would look like. If you decide you want to do this, I would do it as an interaction term, and I would look up additional resources online in order to determine how to properly interpret this beta coefficient here with the interaction term, because that can get a little bit tricky. So just be aware what you're studying when you're looking at subgroup analyses. It's heterogeneous treatment effects between different groups of people, and also what a sensitivity analysis is. So a lot of the time in pharmacoepi studies, you're going to see a lot of different sensitivity analyses, and all these are a series of pre-specified sensitivity analyses that are done after your primary analysis, which can help investigators to understand like how robust their findings are to different assumptions that were made in the study. So you might conduct an analysis if you want to test, how robust is your exposure definition to different definitions of exposure. So, for example, if you only looked at, I don't know, one source of data in order to measure drug exposure, you included an additional source of data in there. You want to see whether your results in your sensitivity analysis, when you include the additional data, is similar to your primary analysis, when you only included one type of variable or data source. So, like I said here, it can include changing the exposure outcome definition. It can include changing the study population. It's just any analysis that's done to support the robustness of your results. So typically, the results of the subgroup and sensitivity analyses appear in the body of the text after the main, in the results section after the main analysis. You can include the full results of the subgroup and sensitivity analyses in the appendix. Sometimes, if these are really important results, you can include them in the tables in the main part of the paper, but that really depends on the study and what the findings of the subgroup and sensitivity analyses are. So I'm just going to quickly show you where the so the sensitivity analyses, the results of that are you include that in the statistical analysis section, and then in the results section, these are at the end here. Yeah, usually it's the last paragraph, so it's in our sensitivity analysis. They actually changed the reference group, it looks like, and they conducted a few other sensitivity analyses. So that usually goes at the end of your study results. But what you want to do in the statistical analysis section is to first outline which sensitivity analyses you're conducting in the first place. So you can see here they had 5 sensitivity analyses in order to confirm the robustness of the results. So finally, I just really want to quickly touch on the fact that there are checklists in order to look at the quality of reporting in observational studies. So these are called STROBE, and this is just a list of criteria that should be included in your study in order to make sure that it's a quality study. So these would be really important to look at when you're preparing your reports just to make sure you're not missing anything. So, in the methods section, what you really want to do is that you should explain how your study size was arrived at, how you measured all of your variables, how they were handled in the analysis. So, did you model variables as continuous or binary or categorical variables? That's really important to explain. You want to describe all your statistical methods. So, you want to describe methods used to control for confounding. So, this, for example, would be adjustment in your Cox proportional hazards model. You want to talk about subgroup analyses and interactions, explain how missing data was addressed, talk about loss to follow-up, stuff like that. So this is just essentially a checklist. Make sure you discuss all of these in your methods section. And then the results section as well. Information you want to include on participants in the results section, report the numbers of individuals at each study stage, give reasons for non-participation at each stage. Descriptive data, we talked about this, give characteristics of the study participants, indicate the number of participants with missing data, summarize the follow-up time, report numbers of outcomes or the risks. Then for the main results, you give unadjusted estimates as well as adjusted or confounder adjusted estimates. Make clear which covariates were actually or confounders were actually adjusted for, and then give the results of your subgroup and your sensitivity analyses. So I'm just one last thing I wanted to touch on, which isn't part of this study, but is part of a few different studies, is sometimes what you'll see is that you'll see a flow chart of patient exclusions. And this is part of this here, the participant section, report the numbers of individuals at each stage of the study. What you'll do is you'll discuss how this patient population was actually arrived at and how many exclusions were made at each step. And this can be included as a little flow chart of patient exclusions. And this is based on your inclusion exclusion criteria. So it's likely good to, you guys probably won't be including that in your reports. You might or might not, depending on the information Patrick gives you, but just be aware that's typically called the flow chart of patient exclusions. I'm just going to you know what, I'm going to open up another paper just to give you a quick example of, I'm just going to look at one of my old papers just to give you a quick example of that. This was a paper that looked at use of diabetes in people with diabetes and heart failure. So this is just an example of a flowchart of patient exclusions based on the inclusion exclusion criteria. So patients with type 2 diabetes, I excluded people using these inclusion exclusion or these exclusion criteria, and then this is the final group of people included in the analysis. And I just gave the numbers of people I excluded at each step. In the RTZD paper, they just present the total study population, but just know that sometimes you can present this flowchart of patient exclusions, and that tends to be an important part of the statistical analysis and reporting study results. So yeah, really make sure that you're covering all of these different points when you're writing out your statistical analysis section, explaining all the descriptive statistics, unadjusted analyses and adjusted analyses, and how you selected confounders in your study. And then the actual results part where you're actually giving numbers and interpretations with respect to participants, descriptive data, outcome data, and your main results and your sensitivity analyses. Okay, so software you can use in statistical analyses. I give the demo in SPSS because it's really user-friendly, it's very basic, it's very easy to use. It's just not suitable for complex analyses. These are some additional resources in order to use SPSS. I would watch these. I give a little demo in another video, but I think that you would probably learn a lot more from people who use SPSS professionally. So just want to quickly browse the demo I give and then actually look at some other demos for some experts, because mine is certainly not an expert level demo, you can go ahead and do that. There's other statistical software you can use. R is really great because it's free. You can also use Stata, that was part of the Solus workspace, I think. You can use SAS and Python. Use whatever you want. There's no perfect software. Whatever you're comfortable with, whatever gets the analysis done, I suggest using that. The only thing is, like, free software like R and Python tend to have more online help just because it's free and more people use it. So that's the end of this data analysis lecture. So if you have any questions, as I mentioned at the beginning of the lecture, please post them on Microsoft Teams or send me an email and I'll post the answers. If you email me, I'll post the question and the answer anonymously, or I'll just answer the question directly on Microsoft Teams. So yeah, make sure you take a look at the SPSS demo and please email me if you have any questions or concerns about the lecture, and best of luck with the analysis section of your study. Hi everybody. So I'm going to do a quick demo using SPSS to help demonstrate how you can do your statistical analysis for your projects using SPSS. So as I mentioned, you can use whatever statistical software you want to use for your analysis. There's lots of options out there, but I think for your purposes, SPSS is very user friendly. It's more point and click. You don't have to do any coding if you don't want to. And that's the reason I'm going to show it in the demo today. So, but feel free to use whatever software you'd like to use. So just to kind of help frame our demo analysis a bit better, I'm going to be using some example data, some simulated example data, to help answer the following research question, which is use of antidiuretics associated with an increased risk of adverse drug events, or ADEs, in the 30 days following hospitalization compared to non-use of diuretics among patients discharged from an acute care hospitalization. So I'm comparing use of diuretics to non-use of diuretics to see whether or not that's associated with an increased risk of an adverse drug event. So I'm just going to quickly go over these steps in the demo. I'm going to import the data, describe the data a little bit, just summarize age, just to show you some of the summaries, statistics and descriptives you can do with that. I'm going to look at the frequency of the outcome, which is adverse drug events, and look at the frequency of the outcome according to exposure. So I'm going to look at the frequency of adverse drug events according to those who did receive a diuretic and those who did not. And I'm also going to quickly show you how to run a Cox proportional hazards model while adjusting for confounders to look at to answer a particular research question of interest. So I'm going to show you guys how to access SPSS from your Solus workspace. So I'm sure you guys are already familiar with your screen sharing. Okay, you're already familiar with this website. So this is your Solus workspace where you can access all kinds of software. So all you have to do is first you have to install the Citrix Workspace app. So you should already have that on your computer. Then you need to log on. So I'm going to go ahead and do that. I'm on a Mac, so this might look a little bit different for you guys. Okay, I need to log in. It's going to ask for my two-factor authentication in a second. So log in. Okay, let me do it on the little app on my phone. Okay. So this should work in a second here. Okay, so then the Citrix Workspace comes up. Cannot use using a smart card. That is not what I want to see on here. Please close your browser. That's very strange. Why is it doing that? Oh, I might have to just close this again. Okay. Well, that's fine. Let's see. Let me do this again. This workspace. Hold Hopefully this works this time. Okay. Should be able to detect. Okay, so detect the app, and then you can open the launcher. Okay. You're not too sure why that didn't work the first time, but that's okay. Okay, so now we can go into the apps. Was something open in the background there? Oh, SPSS is already open. Close. My face is in the way. There we go. Okay, so just go to the apps, which is where I am right now, and then scroll to the bottom. It's in alphabetical order, so you have R there. Okay, SPSS, there you go. So just go ahead and click on that, open it. Sometimes it takes a while to launch it. It's a bit slow. Okay, it's a little bit faster today. Okay, so got our SPSS interface open. So what I'm going to do is I'm going to go to File. So to import the data, I'm going to go File, Import Data. And it's going to be, I don't know what format you guys are getting your data in from Patrick. I think it should be a CSV file, but there's lots of other options there. And if it's in another format like Excel or text data or something, then you can just use those options. And when I have it as a CSV file, so I'm just going to go like that, import as a CSV, and minimize this in the background. Okay, so I have my sample data open here, so you can actually get your data from the O Drive, I think through using this this app on the Citrix workspace. So I don't know where Patrick's going to store the data for you, give you the data, but just know that you can access it through your O Drive, I think. Okay, so I'm going to go ahead and open that. Okay, so it's generating a preview for the data. So just take a look to see whether everything looks normal in terms of, so these are just a list of the variables at the top, and then these are the values for each of the variables for the first row, second row, third row, etc. So this should all be fine. I'm going to press OK. I'm going to go ahead and import my data. So I think I have to double click this to actually see the data. Should open in a second here. Okay, there we go. Okay, so this is my data set open here. Just take a second for all of the data to come up. As you can see, it's just running at the bottom there. Okay, there's all our data. So I'm going to go over to the variable view. So there's the data view where you can see all the data, and there's the variable view. So this might just be easier to start off with. So my first variable here is ID. So that's actually I'm going to stick with the data view, I think. So the ID here is the unique identifier for each patient. So each row in the data shows a different patient, a unique patient. So that's the ID. These are patients who were hospitalized. So the date that they were discharged from the hospital is here. That's our study cohort. What else do we have here? I'm just going to make this bigger. Okay, so we have age. So that little ruler there shows it's a continuous variable. If I go over to the variable view, you can see age units, it's a numeric data. So there's all these different types of variables. There's numeric, date, and string. So string is usually associated with something that's like a name or like has letters in it, and numeric is obviously a number. So just pay attention to that. And then those are some of the characteristics of those variables. So we have ID, age, which is a confounder that I'm going to look at in this analysis. I have sex, which is male or female here. I have their exposure variable of interest, which is use of diuretics, yes or no. It's coded as a binary.
variable, which is coded as a 0 or a 1, 1 for use of diuretics and 0 for non-use of diuretics. I also have use of antihypertensive medications, which is another confounder. I have ADE, yes or no, that's the outcome variable. So that's coded as 1 if you have had an adverse drug event, 0 if you hadn't. I have acute myocardial infarction, which is another variable. It's a confounder. Whether you have renal disease, liver disease, those are two other confounders that I'm going to be looking at. I also have these other variables here, which is ADE date. So that's the date that the individual patient had an adverse drug event on, if they had an event. And so this day of follow-up variable is calculated difference between the ADE date and the discharge date. So we're only following people for 30 days post-discharge. So if they didn't have an adverse drug event, they're going to have a 30 other days of follow-up because they're only followed for 30 days and they didn't have an event. Whereas this person here, they had an adverse drug event 9 days after they were discharged from hospital. So they were followed for 9 days until they had an event. So that's just a quick overview of the data. So what did I have on my list of analyses here? Let's see. Okay, describe the data. Okay, I did that. Okay, so just to show you quickly how we can do some descriptive statistics, I'm going to do a few descriptive statistics for the age variable first. So I'm going to go to analyze, and I'm going to go to descriptive statistics, and I'm going to go to descriptives. And I want to look at age. So you just select it, pop it over into the variables thing, and look at some options. So what do I want? I want the mean. I want the sum. Okay, we're going to look at that first. Standard deviation, min, max, continue. Okay, so I'm going to run that. So that the results for that show up in a separate little output window, which you can see here. Okay, so for age, you can see N, that's the number of subjects that we're analyzing. So we have 226,098 patients. You can see here the minimum age is 18, the maximum is 110. Mean age is 72.8, so 73, and the standard deviation is 14.5. So I think we can also do, let me see here. I think we can also do a mean for this. Maybe just have descriptives. I want to look at. Only letting me look at that's fine. The mean's fine for now. If you want to look at the median, you can also look up how you'd like to do that in your online. I thought that I could do, let me do the frequencies here. Can I do the statistics? Okay, let's see if it'll do the median here. Median with the range, maybe? Let's see what this will do. No. Okay, so that's a frequency, so don't do that. Okay, so that's for categorical or binary variables. So even though you can actually select median in there, it's not actually going to give you the median unless you're looking at a categorical variable. So that's fine. I wonder if I can go in the help. Let's see. Or look something up because I just want to search median. Bootstrapping median subcommand. I don't want it as a subcommand. I want it as a. Let's look this up. So this is how you go about doing a statistical analysis, whether you know the software really well or not. SPSS median. See, it'll show us how to do it here. Analyze descriptive statistics frequencies. That's what I did.
Oh, it must have been at the top there. So I did do it right the first time. I just didn't look at the output properly. Okay, let's go back to that then. Go back to frequencies, statistics. Okay, let's do mean and median. Let's do quartiles, percentile values, standard deviation range. Continue. Okay. Okay, so it actually gives it right there. I scrolled down too far. Okay, so you can see here, the mean again is 72.8, which is what we saw in the previous example. Median is 74. So the mean and the median are quite similar to each other, which suggests that there's not a lot of outliers in the data. Standard deviation is 14, range is 92. And then we have the, oops, scroll down too far here. So the 25th percentile, so that's 67, and the 75th percentile is 83. So that would be the interquartile range for the median, right? The median is 74 with an interquartile range of 67 to 83. So that's just how you calculate the mean and the median, as well as the variability around those, or the variance around those variables, using the point and click options for SPSS. So I think also what I want to do, maybe this is a continuous variable. So why don't we look at a graph? Why don't we try and do a histogram? Chart builder, analyze. Where do we find that? Graphs. Let's see what we can do here. Okay. So I want to do a histogram. I want to do age. Drag gallery. Okay, I'm going to drag age there. I want to do a histogram. Oh, I have to drag the gallery chart. Okay, we're doing that. Age. Maybe I want to do a, no, I want to do no categories selected. Do I drag it? Okay. This is very strange frequency, yes. I'm going to move myself over there. Maybe we should look this one up too. Okay. I think just this goes to show how easy it's going to be for you guys to figure this out on your own, because like I said, I'm not an SPSS user, but I'm really easily able to look up whatever I need to figure out online. So you guys will be, okay, click graphs, legacy dialogues, histogram. Okay, that'll be easier then. So let's get out of that. I was in the wrong one. So graphs, legacy dialogue, histogram. There we go. Okay. So we want to go age, units, variable. Okay, okay, okay. Titles. I think we can leave that for now and see what it comes up with. Okay, let's see what that does. Okay, okay. So that's exactly what we want to be seeing here. So you have to go into the legacy dialogues option in order to do the histogram. Don't go into the chart builder, because it seems like it's just easier to select the graph you need right from the legacy dialogues option. Okay, so what does this histogram kind of tell us here? Okay, so what do we see? There's not very many people who are age 20 to kind of 50, I think this would say, but there's a huge increase in people after the age of 65 there. We have our mean standard deviation for our age at the top. That's our total number of study subjects. So on the x-axis here, we have the age, and on the y-axis, we have the number of times that age appears within our study cohort. So the number of individuals with that particular value of age in our study cohort. So like here, I don't know what that value is there, but it looks like it's around maybe 50. It looks like there's over 8,000 people in our cohort, which are over 50 years of age. So, or about 50 years of age. So that's kind of how you interpret that histogram there. So that's how you do that. What else can we look at here for age? What else did I say we were going to do? Histogram. Okay. So maybe we can do one other just to show you guys. So let's look at, let's look at a scale. Do we have another continuous variable? No. So why don't we do age according to gender or something like that? So why don't we do a box plot of the median age by gender? Let's do that just to show you guys another graph you can do. I just want to do a simple define, okay, variable. So I want to do age, and the category I want to do by gender. Let's see what the options are. Display groups defined by mixing values. No, I don't want to do that. Let's see, okay, what our box plot shows us. So it's just running here. Okay, so that's giving us all the values for our outliers, which I think what you could do is go in and get rid of those. But what we can see here, that's I think the unknown or the other category for gender. So what we can see here is that the median age for females is pretty similar to the median age for males, and the distribution is quite similar. Like there's a higher upper end of the distribution for females, but the lower end is quite similar. So you can demonstrate that with a box plot, because age is a continuous variable and you're categorizing it according to this binary or three-level variable if you want to compare between the two groups. So that's another descriptive statistic or graph that we can look at. Okay, let's move on then to our outcome variable, the frequency of our outcome variables. So just recall that our outcome variable is an adverse drug event. So that's our variable here. Where did it go? ADE, yes or no. So what I want to know is how often that happens in our data set. So I'm going to go back over here. I'm going to go analyze descriptive statistics. I'm going to go to frequencies. I'm going to put that back over there. I'm going to find age. I'm going to put age or ADE, yes or no, put it over there. I'm just going to, are there any charts I can do for this? Bar charts, pie charts, histograms? No, I don't want to do that format. No, let's just leave it for now. Let's see what it gives us. The best thing to do to learn how to use the software is just to play around with it. Okay, here's our little table here. So what we have here is that the total number of people in our study cohort, 226,000, is there. The 0, that's the people without an adverse drug event. So that's about 93% of our study cohort. Then we have about 14,983 people with an adverse drug event. So that's about 6.6% of our cohort. So that's really important to understand that about 6.6% of patients had an adverse drug event. Okay. So that's fine. Now, what I also want to do is look at whether I want to look at the risk of adverse drug events according to the drug exposure category. So let's do that. Tables. I'm going to go to descriptive. Okay, I'm going to go to descriptive statistics. I'm going to go to cross tabs. So I think I want my row to be adverse drug events. That's the outcome that goes there. And then I want to look at that according to diuretic, yes or no. That's the column. Okay, I think let's do it with a chi-squared statistic just to see what that gives us. Continue. Let's see if it'll give us the, okay, so, oh, I want to switch those around. Okay, we're going to go back and do that. Oh, back to the cross tab. So I want 80E at the top. Oh yeah, okay, that's fine. So we're just going to switch those around. So we're going to have diuretics over here for the rows, and then 80E yes or no for the columns. Okay. Yeah, that's what I wanted. Okay, so what we can see here is a cross tabulation of who falls into each of these cells according to who had an outcome, no or yes, and then who had a diuretic, no or yes. So so we want to know among people who didn't have a diuretic what the risk of an ADE was. So that's going to be 14,436 divided by 218,201. That's going to be the risk of an adverse drug event among those who were not exposed to a diuretic. And then we're going to calculate the risk of ADE among those who were exposed to a diuretic as 547 divided by 7,897, and that'll give you the risk of an adverse drug event among those who were exposed to a diuretic. You can also calculate the risks or the rates rather for these variables, but you'll have to look up. I'd look up the command on how to do that online. So that just gives you the cross tabulation for that. And so the chi-squared just gives you, oh, I don't even have that there. That's fine. It's a Fisher's exact test. Okay. So that's what I wanted to show you for that. Okay, frequency of outcome according to exposure. Yes, that's just what I showed you. Okay, now I'm just going to quickly show you how to run a Cox model. So I showed you to do some quick descriptive statistics on your confounders. I showed you how to look at your outcome variable, your outcome according to your exposure variable. And now I'm going to show you how to run quickly a Cox proportional hazards model. So remember that a Cox proportional hazards, I'll show you how to do logistic regression. Well, you can look up logistic regression yourself online because that's the more simple version. I'm going to give you the more complicated Cox model. So remember, these models are used when you have time to event data. So what I'm going to do is I'm going to go to analyze. I'm going to go to, where is it? Survival. There it is, survival. I'm going to go all the way down to Cox regression. So you're going to have to specify your time variable. So I've already done that. That's the days of follow-up variable. You put that in there. Status is the event. So you're going to put ADE yes or no in there. I'm going to define event, single value. So ADE equals to 1 is how you define the event. So you add that in there. You go continue. Covariate. So my confounders for my model, I'm going to choose a few of these. It's going to be age. It's going to be gender, acute myocardial infarction, renal disease, and liver disease. I think is what I'm going to choose for now. Okay, I'm going to go ahead and run that. It's running. Okay, so this is your output for your Cox model here. So these are your Oh, I wanted to include the confidence intervals. Okay, so go back. I'm going to go back just because I didn't include the confidence intervals. Go back into my Cox regression. I think I have to go into the options. Okay, and click if you want the confidence intervals for the hazard ratios, which are going to be produced by your Cox proportional hazards model. You have to go in and click that there. Press continue. Okay, so I'm just going to rerun that quickly. Okay, there we go. So just as a reminder, Cox proportional hazards model produces hazard ratios, and this is what the EXPB column here represents. So the beta coefficient is not the hazard ratio. You have to exponentiate the beta coefficient in order to get the hazard ratio, which is what this is here. And then this is the confidence interval for the hazard ratio. So did I forget to include my exposure variable? I believe I did. Right, okay. I forgot my exposure. I just included my my covariates in there. Okay, that's fine. I'll just add that to the bottom. Diuretics, add that in. It has to be part of your covariate section as well. So okay. Okay, I think we're almost there. There we go. Okay, so these are the hazard ratios for all my other confounders up until that point. This is my diuretic variable here. So if we follow that along, you can see here, okay, we can see here that the hazard ratio is 1.01 with a hazard ratio from the confidence interval spans from 0.93 to 1.1 if you're rounding it up. So based on this, I would interpret that row as use of diuretics is not associated with an increased risk of adverse drug events following hospitalization after adjusting for all these patient confounders, including age, gender, AMI, renal disease, and liver disease. The hazard ratio is slightly above 1, so it's 1.01, but the confidence interval spans the null, which is 1. So that just shows that there's no actual association between use of diuretics, which is my exposure variable, and my outcome of interest, which is adverse drug events in 30 days after adjusting for patient confounders. So that's just a really quick general overview of Stata. Obviously, using Stata isn't my strong suit. That's not the statistical software I use, but I haven't used it in like 8-10 years, I think, and I was able to pick it up again really easily just now. So just to show that you guys will very easily be able to do whatever you need to do in SPSS. It just might take a little bit of Googling, which I did in the demo, which is really, really easy. And yeah, I'm sure you guys will be able to figure out your analysis quite easily. So yeah, that's just a quick demo. Not a great demo. There's other much better demos online. So I think I provided some links for those in the lecture slides. So I suggest you watch those to actually see an expert figure out how to teach you SPSS. So that's it. You can post any questions you have about this demo as well in Microsoft, not in MS Teams. Yes, in MS Teams in the forum. So okay, good luck with your analysis, and hopefully we'll be able to see you guys online soon. Okay.